Good afternoon, everyone. So this is my next lecture based on PN junction diode, which is in continuation with the lecture number 15. So in the last lecture, what we have seen that we have seen about types of PN junctions and how with the help of the PN junction diode, we can form our BJT, that is bipolar junction transistor, which is basically mainly of two types, that is of NPN or PNP type. So in the last lecture, we have seen the basics of BJT, that is bipolar junction transistor. It has two types, that is PNP and NPN. How the currents will flow from P to N side in both the transistors, and what are the different advantages of using BJT in our applications, in our semiconductor devices. So in this lecture, we are going to see how this can be evolved further. So in the last lecture, we have seen about how the common collector configurations are there, common collector configuration, and in that configuration, how we can see the DC mode. So in the DC mode, the level of IC and IE due to the majority carriers are related by a quantity which is called as alpha. So here there is a quantity which is called as alpha, which is basically, because we have seen that is for the transistor. If we draw like this is for PNP type of transistor, and we have this type of figure. So the current will flow from here. So we have emitter, base, and collector. So the current will flow from P to N side. We can see here. So how can we find out the value of alpha? So alpha is basically the collector current divided by the emitter current. So here IC is your collector current, and your IE is what? Emitter current. So it can then be summarized to IC. So from here, because it is alpha is IC by IE, so we can write IC as alpha into IE. So it can be summarized to this value, that is IC is equal to alpha into IE, ignoring the common base basic difference current due to the small value. So for AC situations where the point of operation moves on the characteristic curve, and AC alpha defined by this point, that is alpha is equal to delta IC upon delta IE. So sometimes we have the dynamic type of gain and a static type of gain, and that gain is defined here for alpha, that is a static type of, which is IC by IE, and for the dynamic type it is delta IC upon delta I, which we can find out with the help of the characteristic curve. So alpha common base current gain factor that shows the efficiency by calculating the current percentage from current flowing from emitter to collector, and this the value of alpha is typically comes out to be 0.9 or it is around 0.998. So either it can be a PNP or an NPN transistor. We can easily find out the value of alpha by getting the value of IC and IE, which is your collector and the emitter current. Obviously, IC comprises of two types of current, that is the emitter current and the common base reference current. So for the case of the common base configuration, we can find out like this. So here we are coming to the biasing part of the BJT. So proper biasing common base configuration in active region is approximately given by IC, which is equivalent to IE. So here we are taking common base configuration. That's why I have taken IB, which is the base current, to be grounded, which is equivalent to 0 microampere. So that's why if you see the pictures below, we are having the common base configuration. So the base is common to collector and emitter. So we have the voltage between VBE and the current basically is IC, which is the collector current. So for the PNP type of transistor, if it is PNP type of transistor, the current direction is from P to N side. Obviously, we have two voltages, that is for the collector side it is VCC, and for the emitter side it is VEE. So we have applied here negative voltage, negative terminal to P side and positive to N side. Similarly, we have positive to P side and negative to N side. So thus we have this type of configuration for the biasing. Next we have for the NPN. So for the NPN, same thing is there. So we have emitter base collector configuration, and we have VEE and VCC. So this is the VCC for the common collector, and for the voltage it is VE. So it is again grounded. The common base part is again grounded, and we have this type of configuration. The current flow from in the PNP type of transistor is from P to N side. So that's why the current direction is from P to N side. That's why it is IC is in the upward direction. Similarly, I is in the upward direction. In the same way, we have this is NPN. That's why the current direction is from N to P sides. So next we have common emitter configuration. So it is called common emitter configuration since emitter is common or reference to both the inputs and output terminals here. So emitter is usually the terminal closest to or at ground potential. Almost all amplifier design is using connection of common emitter nowadays to the high gain for current and voltage. So as we have already discussed about common base configuration, the next one is a common emitter, which is usually used in amplifiers design. So two sets of characteristics are necessary to describe the behavior for common emitter, which is input base, this basically base terminal, and output, which is the collector terminal parameter. So we will see how the common emitter configuration has different parameters in the next slide. So proper biasing common emitter configuration in active region is given here. So in the first diagram, we have NPN type of transistor, and we have taken here common emitter configuration. That's why the emitter is to be grounded, and the voltage is provided between the base, that is VBB, and similarly the voltage is provided at the collector, that is VCC. So here positive is connected to N side and negative is connected to again N side. Similarly here positive is connected to P terminal and negative is connected to N terminal. So we have the base current that is flowing from the from positive to P side. Obviously it is IB. Similarly the collector current is input to the collector side, that is IC, and here it is IE. So overall the picture is clear, which we can see from the next diagram, that is we have a NPN type of transistor. This is NPN type of transistor, and we have emitter is grounded. So it is common emitter here. So emitter is grounded. So here the voltage provided at the emitter is ground is equivalent to 0. VBB is the voltage provided to the base, and VCC is the voltage provided to the collector. So next we have a PNP type of transistor configuration. In the same way we can draw for the PNP transistor configuration as in the earlier case. So in the PNP transistor configuration we have voltage VBB that is applied between base and emitter. Similarly VCC is provided between base collector and emitter, and the emitter port is grounded. So here negative is connected to with the negative, and positive is connected to the positive. That's why it will be in forward biasing. Similarly the negative is connected to the positive and positive is connected to positive, then it will be in reverse biasing. So we have a clear picture of the common emitter configuration in the PNP transistor configuration, that is like this. So the current direction, that is from IC to because it is PNP type of transistor, so the current direction is from P to N side. So the current is up outward side from the collector. Similarly the emitter has a input current. Similarly the base has the output current. So we can see the input characteristic for a common emitter NPN transistor. So we have basically common emitter configuration is there. So we have fixed the voltage for the common emitter case, that is for 1 volt and for 10 volt and for 20 volt, and we have drawn the characteristic curve between VBE and IB. So in the X scale we have distance of 0.2, 0.4, 0.6, 0.8 and 1.0 scale. Similarly in the Y axis we have 10, 20, 30, 40, 50, 60 and so on 100 scale. So when you draw up to certain point, obviously that is for the knee voltage. So this is your knee voltage as in the PN junction we have seen earlier. So for the knee voltage the current is usually 0, and when you increase above the knee voltage the current usually rises up. So for 1 volt the current is sharply increased, and for 10 volt it is increased much higher, then for 20 volt it is increased above than 10 volt. So for all the voltages for the common emitter configuration we can see easily the difference between the current, that is the base current. So this is the base current, which is IB, which you can see that is for 1 volt, for 10 volt and for 20 volt it is different. So here we have IB which is in microampere compared to milliamperes of IC. So IB will flow when VBE is greater than 0.7 volts. So for silicon it is 0.7 volts and for germanium it is 0.3 volts. So which is your new voltage. So for silicon and for germanium it is 0.3. Therefore this value of IB is very small and there is no IB at all. Base emitter junction is forward biased here. So whenever you do the common emitter configuration, whenever you see the common emitter configuration, obviously the base emitter junction is to be forward biased and the emitter collector junction to be in reverse bias. So increasing VCE will reduce IB for different values. So when you increase the value of the common collector emitter voltage, so that will obviously decrease the value of the current for the base. So IB will gets down when you increase the voltage. So when you increase 1 volt, when you taken 1 volt, then you have taken 10 volt, then again you have taken 20 volt. So for 20 volt, the value of the IB is lesser as compared to the 10 volts. So now the output characteristic for a common emitter NPN transistor. So here we have 3 regions again. We have already discussed, that is the first region is active region, the second region is cutoff region, and the third region is saturation region. So we have a curve between VCE and IC and the base is common, that's why the current for the base is here 0 microampere, then 10 microampere, then 20 microampere, then 30 microampere. We are exceeding the current from 0 to 60 microampere. So below 0 microampere, there is a region which is called as cutoff region. So this region, this below 0 microampere region is cutoff region. So less than 0 microampere, this region is basically cutoff region. So, and above between VCE and the value of where the current is increasing, the region is called as saturation region. So this shaded portion is called as saturation region. Next, we have an active region from where the current will keeps on rising. So the current will keeps on rising after the new voltage. That's why the region is called as active region, and that region is basically a linear region. So for a smaller VCE, that is VCE is less than VC saturation, IC increases linearly with increasing of VCE. So for VCE is greater than VCE saturation, IC not totally depends on VCE. That's why the IC that the collector current is basically constant here. Next we have IB, which is in microampere, is very small compared to IC, which is in milliampere. Small increase in IB causes big increase in IC. So when you increase IB value, there will be a sharp increase in the value of the IC. Next we have IB is equivalent to 0 and ampere, and that's why ICEO means the collector emitter current occurs here. So noticing the value when IC is equivalent to 0 ampere, there is still some value of the current flow. So that's why the region below the IB is your cutoff region where there is no current flowing. The region just above the 0 volts and less than VCE saturation is called your saturation region, and the region which is above the VCE saturation and above IB is equivalent to 0 microampere is your active region. So these are 3 regions which can be defined in any configuration. Either it can be a common emitter, common collector, or common base configuration. So on the basis of these parameters, we can divide these active regions, or these regions. That is the first one is the active region, the second one is the saturation region, and the third one is the cutoff region. So here BE, that is the base and emitter junction, is forward biased in the active region. Collector base junction is reverse biased in the active region. And lastly, it can be employed for voltage, current and power amplification. So normally active region is used for power amplifications, that is for voltage, current and power. The second one is the saturation region. So here the base and emitter and collector and base junction is forward biased. Thus the values of IB and IC is too big here. So the value of VCE is so small in the saturation region, and the suitable region when the transistor is acting as a logic switch. So this region is usually used for a logic switch. Not and avoid this region when the transistor used in as an amplifier. So whenever you are using transistor as an amplifier in the active region, you cannot use it as a saturation region or as a logic switch. Similarly, in the cutoff region, what will happen? The region below the IB is equivalent to 0 microampere, which I have shown you in the earlier diagram, is to be avoided if an undistorted output signal is required. So here, base and emitter junction and collector and base, both the junction is to be in reverse bias. As in the earlier case, in the active region, we have base and emitter junction is forward and collector and base junction is reverse bias. In the saturation region, both should be on forward bias, and in the cutoff region, base emitter junction is forward and collector and base junction both should be in reverse bias. So here IB is equivalent to 0, obviously, because both the junctions are in reverse bias. IC is not 0 during this condition, and that's why IC is equivalent to ICEO. Where is the current flow when base and emitter junction is reverse bias? So in the below diagram, we can see that for base open collector to emitter, we have IB is equivalent to 0. So here next parameter is your beta. The first parameter is alpha, the next, which is IC upon IE, and the next parameter is beta or amplification factor. So the ratio of DC collector current, that is IC, to the DC base current, that is IB, is your beta, which is DC current gain, where IC and IB are determined at a particular point, which is called as operating point or Q point or quiescent point. So it is defined by the following equation, that is beta DC is greater than 30 and less than 300. So here there is a pyramid type of structure which shows beta DC, IB and IC. So on data sheet, we can find out different values of beta DC with the help of the H parameters, with H is derived from the AC hybrid equivalent circuit. So here the value of the FE are derived from the forward current amplification and common emitter configuration respectively. So with the help of alpha and beta, we can design our transistor or any particular application which is used for amplification or for digital circuits. So for AC condition, an AC beta has been defined as the changes of collector current, which is IC, compared to the changes of base current, which is IB, where IC and IB are determined at a particular operating point. So on data sheet, we can find out that beta AC is equivalent to HFE, and it can be defined by the following equation, that is beta AC is equivalent to delta IC upon delta IB. So by this way, we can define our alpha and beta for the common emitter configuration. So here there is a slide for having a relationship between alpha and beta. So the case 1 is, what is IE? IE is your emitter current, which comprises of two currents, which is IC and IB. So when you substitute IC is equivalent to beta IB into this, so what you will get, IE is equivalent to IC plus IB. So we have to put here IC is equivalent to beta IB, and when you put here this value, that is beta plus 1 IB. So this equation is important, which having a value of IE, which is the emitter current, in terms of base current, which is equivalent to beta plus 1. So this is the equation. This is the case first. The second case is having alpha value, which is alpha is equivalent to which we have already defined, that is alpha is equivalent to IC upon IE, or IE we can define as defined as IC upon alpha. Here again beta is your IC upon IB, which is between the ratio between the collector current and the base current, and IB, which we can define like this also, that is IC upon beta. So when you substitute equation number 2 and 3 into 1, so this equation is your first equation, which is I is equivalent to IC plus IB. So when you substitute these two parameters, that is I is equivalent to IC upon alpha, this value IC plus IB is IC upon beta. So when you substitute this, you will get your relationship between beta and alpha. So there is two relationship. first one is the alpha. This is alpha is equivalent to beta upon beta plus 1, or we can write as beta, which is beta is equivalent to alpha upon 1 minus alpha. So by this way, in numerical problems, we can find out the value of the alpha and beta by getting the value, by having the value of IC and IE or IC and IB. So with these two equations, we can find out the gain for the emitter and for the collector. So next we have common collector configuration, which is also called as emitter follower. So it is called as common emitter configuration, since both the signal source and the load share the collector terminal, a common connection point. So the output voltage is obtained at emitter terminal here. Obviously, the input characteristic of the common collector configuration is similar with common emitter configuration. Here, common collector circuit configuration is provided with load resistor from emitter to ground. So it is used primarily for impedance matching purpose, since it has high input impedance and low output impedance. So these are some points for the common collector configuration. How can we draw the common collector configuration? We can see from these figures that we have PNP or NPN type of transistor. So here the collector is to be common. The current is in between the base current, or the voltage is VBB. Similarly, the voltage for the emitter is VEE. Or we can draw like this a schematic, that is for PNP. This is PNP. The current is from P to N side. So emitter port, terminal is upward and collector is downward. So we have IE current, IB current and IC current. The same relation holds here, that is I is equivalent to IC plus IB. Similarly, for the PNP, NPN type of transistor, we have the collector current, the base current and the emitter current. You just check out the direction of the currents according to the polarity. So wherever there is negative terminal, obviously the current will flow from P to N side. Then again, for the collector, it is from P to N side. Similarly for the base. So we have a configuration or symbol notation like this for the NPN type of common collector configuration. So these configurations will give you the overall picture about common emitter and the common collector and the common base configuration. So similarly, in the same way, we can plot the characteristic curve for the common collector configuration. So here we have again the three regions, that is the active region, the cutoff region and the saturation region. So we have the characteristic curve between VCE and your IE. So VCE is in volts and IE is in milliampere here. The base current is IB is equivalent to 0 microampere, 10 microampere, 20, again 30, 40, 50 and 60. So when you start increasing your VCE, that is common collector emitter voltage, then there will be a change in the current. So after the knee voltage, there will be a sharp increase in the current. Before the knee voltage, there is a saturation region, and below the value of the IB, which is 0 microampere, there is cutoff region. So in the same way as earlier, we have a drastic change in the current when you increase the emitter current, when you increase your base current from 0 microampere to 60 microampere. So next we have limits of operation. So many BJT transistors used as an amplifier. Thus, it is important to notice the limit of operation. So at least 3 maximum values is mentioned in data sheet. There are maximum power dissipation and at collector, which is PC max or PD. There is maximum collector emitter voltage, that is VCE max, sometimes named as VBR, or maximum collector current, that is IC max. So there are few rules that need to be followed for BJT transistor used as an amplifier. The rules are: transistor need to be operated in an active region. So IC is less than IC max here and PC is less than PC max here. So these are some limits of operation when you draw the characteristic curve or your biasing thing. So here we can see that is the curve between VCE and IC. We have different currents, that is again IB is equivalent to 0 microampere, 10 microampere, 20 and 30 and then 40, 50, 60. We have a cutoff region just below the value, that is IB is equivalent to 0 microampere. We have a saturation region just below the value, that is VCE saturation, and the active region, that is in between the currents. So we have again rise in the current when you increase the voltage, that is VCE in volts. So there is some point where it is shown as ICEO, so which is collector emitter current. So with this we have some operating points, this point, this point, this point. So this point, which is represented as PC max, this is the maximum power point at the collector, which is equivalent to P is equivalent to V into I. So that's why it is given as VCE into IC. If you check with the numbers, it comes out to be 300 milliwatts for this type of graph. Similarly, there is a point that is IC max here, this point, which is shown here as 50. So this point having the value, because it has a value of VCE. If you see, the value of VCE is around 10 and the value of IC is around 30. So 30 into 10 is equivalent to 300 milliwatt. Similarly, there is a point here. So these are some operating points which you can see in the graph. So with these operating points, we can see from where to where there is an active region, there is a cutoff region, or the current, how the current rises as you increase your VCE, that is the voltage between collector and the emitter. So VCE is at maximum and IC is at minimum, that is IC max is equivalent to ICEO in the cutoff region. So IC is at maximum and VC is at minimum in the saturation region. The transistor current operates in the active region between the saturation and the cutoff. So between the saturation and the cutoff, it will act as in the active region, or we can use as an amplifier here. So thank you so much. In the coming lectures, what we will see about how the BJT, these configuration, that is common collector, common base and common emitter configuration, can be used in various industrial applications, where we can easily manufacture our different type of amplifiers or logic design circuits with the help of these configurations. So these basically is giving you an idea about how the transistor can play an important role in today's era, and how these can be evolved as an chip making. So because in the FPG or in other advanced chips, we can use these transistor circuits as a product, as a mini product in a particular configuration. So we will see about how these transistor configuration evolved in the different industrial application, and then we will look after other diodes like impact diodes and other semiconductor diodes. So in the meanwhile, we will also see about how the LEDs and lasers are working in today's era for the purpose of the generation of the light and for the detection of the light. Thank you so much.